Hello everyone, I'm Xinzhang from Stony Brook University. I'm going to talk about our paper. It's joint work between Stony Brook University and the University of Paris-Saclay. Whole slide images are very large, which makes end-to-end classification difficult. Conventional approaches tile the image into patches and aggregate all the patches to predict the final label. Note that the feature extractor in this pipeline cannot be fine-tuned because there is not enough GPU memory. Conventional multiple-instance learning-based approaches are slow because tiling is slow. They lose the spatial relation information of the tiles as each tile is processed individually. They are less accurate compared to end-to-end training because pre-trained features cannot be fine-tuned in previous approaches. Locally supervised learning is an alternative to the end-to-end training pipeline. It divides the network into several modules and trains each module locally. This means that we need much less GPU memory. We can process whole cell images entirely in GPU without any tiling. Compared to multiple instance learning-based methods and end-to-end training, locally supervised learning fades into memory and at the same time is fast and accurate. We propose a novel locally supervised learning scheme that requires much less memory during training. In this way, entire whole cell images fit into the GPU. During inference, our framework is super fast because we avoid tiling. At the same time, we also outperform sorted methods because we are able to use fine-tuned features. We also propose a random feature reconstruction model to improve the accuracy with negligible GPU memory cost. Let's look at our framework. The original network, for example ResNet34, is divided layer-wise into K modules. A module can contain any number of layers. For instance, module 1 in our setup contains the first 6 layers of ResNet34. The entire input image goes into module 1. Then, an auxiliary model computes a loss function so that module 1 can be trained locally. After that, we release the GPU memory occupied by the computational graph of module 1. The output of module 1 becomes the input of module 2. From now on, there will be no more updates of the gradients of module 1. We will repeat this approach for all the other modules except the last module. The last module is trained together with the classifier that produces output labels without any auxiliary model. Our final classifier consists of an attention pooling layer and a fully connected layer. Finally, here is the complete framework. Let's look into the auxiliary model, the key component of our method. For an example module shown here, the output is the current feature and the input is the previous feature. Both of them are the inputs of the auxiliary model. The auxiliary model has 2 branches. The upper branch uses an auxiliary classifier to predict the labels of whole cell images. The structure of the auxiliary classifier is similar to the final classifier. This branch computes a classification loss. The lower branch is the IFR model. It takes both the current and the previous feature as input. This branch computes the reconstruction loss. Let's talk about our IFR model. First of all, why do we need it? In a recent accurate paper, one author shows that the image reconstruction loss can avoid performance degradation of locally supervised learning. However, their method does not work in our scenario because we cannot reconstruct the entire whole cell images due to memory limitations. For example, for a slide that has 23,000 pixels times 10,000 pixels, the required memory is larger than 45 GB, which is beyond the memory of most GPUs. So we follow the practice of one author and propose a random feature reconstruction model which is both accurate and efficient in memory usage. Let's look into the structure of IFR model. Its inputs are the current feature and the previous feature. As the entire whole slide image is pretty large, we cannot reconstruct the whole slide at the same time. We only reconstruct features instead to reduce memory consumption. Still, the feature map is too large in the early network stages, so we need to sample patches at the corresponding spatial locations for the current and previous features. Then we use the reconstruction model that takes as input the sampled current feature and reconstruct the sampled previous feature. We compute a reconstruction loss between these two features. For modules except the last module, the total training loss is the addition of the classification loss and the reconstruction loss. Alpha is the regularization width. In the last module, we only use the classification loss. We use cross-entropy as classification loss and the MICCAI loss as the reconstruction loss. We test our approach on 3 whole cell image datasets: the TCGA non-small cell lung cancer, the TCGA renal cell carcinoma, and the liver kidney stomach datasets. The first is a binary classification, and the other two are multi-class classification datasets. We use a 5x magnification for all the datasets. The first advantage of our method is that it significantly reduces GPU memory consumption during training. We compare our method with end-to-end training on whole cell images that have 3 typical sizes. When our network is divided into 4 parts, our method needs only 30% of the memory needed for end-to-end training. When our network is divided into 8 parts, we need only 20%. Because we need so much less memory, we are able to fine-tune the pre-trained features and actually improve classification rates. We compare the testing accuracy of our methods with the number of SOTA multiple instance learning-based methods. Our results show that our method is 2 to 5% more accurate than the best multiple instance learning-based methods. When it comes to streaming CNN, which is the previous whole slide level method, our method is 1 to 3% better. If we increase the number of modules to lower memory consumption, we get almost the same performance. For example, when we use 8 modules, we save 10% more memory and lose less than 0.5% accuracy compared to the 4 module case. This proves the robustness of our method. Our method is not only accurate but also fast. We compare the inference speed of our method to a popular multiple instance learning-based method, Gambio. We are 7 to 10 times faster on whole cell images of 3 typical sizes because we avoid tiling the images. An ablation study on the IFR model shows that it improves accuracy by 1 to 3%. Now let's visualize some of the highly attended regions during testing. These attention maps come from the attention pooling layers of the final classifier. We can see that the highly attended regions identify meaningful regions like tumor regions. In conclusion, we presented a novel locally supervised learning framework for the classification of entire whole cell images that can fit in a GPU. Extensive experiments show that our method is accurate, fast, and saves GPU memory. We show the great potential of locally supervised learning on classifying whole cell images. We hope it can be extended to segmentation problems in the future. Thank you for listening. Our code is publicly available online. We will be both online and in person at poster T49 in an hour. We would love to tell you more about our work. Thank you.